Well, thank you. Can I start? Yeah. Good, good. Right, okay, well, first of all, thank you very much, everybody. Thank you for inviting me. I'm just going to start a timer here so I can keep on track. What I'm going to be talking about today is something that we don't naturally think about. We're going to talk about carbonates and carbonate communities that develop and in fact thrive in volcanic settings. So my sort of subtitle here is carbonates. You can't basically keep a good carbonate down. They do survive with volcanoes throughout geologic history. Today, you can find carbonates growing in association, developing in association with volcanoes around the world. But when we go to our stratigraphic record, we find throughout the entire stratigraphic record, you will find carbonates developing or developed alongside volcanism. And I took this screen grab this morning from the Smithsonian institution's website, and there's currently today, there's 48 active eruptions on the planet, and that's about the norm. The norm is around about 46 to 50 eruptions on any day of the year. And you can see that many of these volcanoes are in tropical settings. You've got many volcanoes here in Indonesia, in Central America, in the Caribbean. And these areas of volcanism are, of course, areas of carbonate accumulation. So carbonates have been developing in association with active volcanism throughout the geologic record. Yet they are much undocumented, let's say. And many people would think, oh, there's only negative impacts. In fact, there are many positive impacts of your carbonate in developing in tandem with a volcanic system. First of all, volcanism quite often produces very stable substrates. As we know, many carbonate communities, many benthic carbonate communities need a nice stable substrate on which to grow. Volcanoes create bathymetric relief. The volcanic edifice itself, or lava flows associated with the volcanic edifice, the volcanism, will produce bathymetric relief. This is very useful for carbonates. They like bathymetric relief. It might push them up into the photic zone. Volcanism, particularly the hydrothermal fluids associated with volcanism, are an important source of solutes and nutrition to the organisms that are associated with the carbonate communities. It's all not positive though. I'm afraid there's a lot of negatives. Total obliteration is the biggest negative, and we'll look at that in a minute. Burial, temperature rise, ingestion of glass. Not very nice to eat glass. That's a big problem for many organisms, particularly filter feeders. pH, the list is pretty much endless. There are many, many negatives as well. But despite this, carbonates do thrive. This is perhaps, or until recently, was one of the largest recent sub-recent volcanic eruptions that we have well documented. And this was the Krakatoa 1883 eruption. And this was a nice example of obliteration. Nothing survived this. The entire island was pretty much lost. And we can read about that. You'll see many books about it. You can even watch a film about it. But what they don't document is what was happening in the sea around that island. There was beautiful coral reefs, fantastic atolls all around that island, little patch reefs rather, and all of those were totally wiped clear. During this eruption, basically the sea itself was pushed back by the eruption, and the whole area was scoured down to several meters. There was nothing left of the carbonate community. And this has got to be what happened at many, many points in geologic history. There's many, many, many coral communities, sponge communities, carbonate communities that we will never know about because they were totally wiped out during the volcanic event. Not quite as serious, but still fairly serious, is burial. Carbonate communities that actually get buried. So there's two basic modes of burial. First of all, you can be buried by lava, and secondly, you can be buried by pyroclastic material. If you're buried by lava, this is not so good. Lava, by its very definition, is incredibly hot. Now, of course, if you are a a mobile organism, for instance, the sharks or fish or lobsters shown in this image, you can all run away. You can exit stage left. You can make your escape. But sessile organisms do not have this luxury. They will simply be buried, and usually mortality will ensue. Now, I say usually because you'd think anything that's buried by red hot lava flows is going to be killed. But in fact, there are survivors. Water is a very good insulator. And that top chilled margin of the lava flow is also a good insulator. So in fact, you will have coral polyps and other organisms surviving only a few centimeters. In the case of Hawaii, where lava flows have entered the sea and basically changed into pillow lavas, we have polyps documented only 7 centimeters away, surviving quite happily. And once this lava flow has stopped, has cooled, those polyps become areas for regrowth. So this coral community here, yes, everything down here in the bottom, everything in the bottom within the lava flow will die, mortality. But those little branches that are sticking above that lava flow, they have a chance of survival and regrowth after the eruptive event. Another form of burial is by volcaniclastic material, by loose volcaniclastic material. Now, the nature of what's going to happen to that carbonate community is going to depend on the rate that material comes in, the amount of material that comes in, how long that material is coming into the environment, the grain size and other characteristics of that material, the prevailing energy, and indeed the actual types of organisms that are present. So I'd just like to take some examples here. Where we have a small amount of volcaniclastics, as you can see in this first bit of the panel, with a small amount of material coming in, organisms that can self-exhume will manage to literally dig themselves out of the problem. In high energy settings, they may actually be exhumed by current action or wave action, removing material. They may be excavated. As long as this happens within a few days, there is a good chance of survival. Organisms like corals or any upstanding organisms that manage to project above that new sediment surface, yes, they will die with the lava flow. They'll die in their lower portions, but the upper portions can survive. So we can get corals, we can get sponges, we can get elevator species continuing to grow in a synstratal relationship. However, if we have continued input or we have a large amount of material input, then we can have the problem of full burial, and that was going to result in a mass mortality event. Usually organisms die either from anoxia or starvation. Starvation seems to be the most common cause of mortality. So basically they are buried, they can still effectively breathe, but they just haven't got anything to eat. And within a few days, maybe a few weeks, these organisms will actually starve to death. So not a particularly nice way to go. And eventually we may have a new community developing on the surface of this new sediment. And I'm going to come back to that in a little bit when we think about community structures. Turbidity is a very large issue. Turbidity is a very large issue. And the main impacts of turbidity, that's sediment suspended within the water column, is first of all, it darkens the water column. So it reduces light, effectively shallows the euphotic zone. And the second big problem is that material that's suspended in the water column can be ingested by organisms, and that, particularly for volcanic glass or fragmentary material, is a big problem for lacerating or clogging up their guts, which is going to again result in mortality. Now, the big controls here are the proximal to distal effect and the nature of the material. Is it primary or secondary? Closer to the source of the material, we'll get coarser grain material. Further away, we'll get finer grain material, obviously. Primary material is the material that's directly input to the marine system, whereas a secondary material, that's material that's coming into the marine system through weathering. So that might be quite often finer grained because it's converting quite rapidly. The volcanic material converts to clays and produces lots of muddy clay, fine grained material. So here's an example of this. This is the scene of, this is Anak Krakatau. So this is Krakatau, and this is the original sort of island was about here. And this is Anak Krakatau, which translates to child of Krakatau. And this is an image in 2014. 2 years later, 2 or 3 years later, in 2019, or in fact late 2018, we had a massive eruption. And you can see the scale of this eruption. First of all, Anak Krakatau has grown. And secondly, you can see the devastation to this island, small island to the east of Anak Krakatau. But what I want you to focus on here is the actual material entering the water column. You can see that this is material that's in suspension. It's being eroded from the flank of the volcano, and it's being picked up by the prevailing currents. And this is where currents and energy are very important. They can keep material in suspension many, many years after the volcanic eruption itself. So you see this material peeling off the volcano and being carried towards the east, where it's actually entering the straits between Java and Sumatra. And in those straits, you can actually see beautiful vortexes building up with that current. Here's another example, and this is an example some of you may recognize from the news this year. This is Hunga Tonga Island in the left-hand side of the image, and in the northeast of the image, we have Hunga Ha'api. And these were two islands sitting there quite happily just north of Tonga back in 2014. In 2016, there was a pretty major eruption between the islands, and this eruption was focused towards, it was actually between the islands, and it joined them up, and it was focused in terms of energy and in terms of prevailing currents and in terms of prevailing wind direction towards the southwest. And you can actually see those currents still carrying material towards the southwest. This new island joined together is now called Hunga Tonga, or was called Hunga Tonga, Hunga Ha'api, just joined the island names together. But what was very interesting here, even though it is less than a couple of kilometers away, this area here was in a blast shadow. The high cliffs that you can see in the northeastern island, those high cliffs basically formed a barrier to the eruptive event. And those reefs, those coral communities in that northeastern sector all survived the eruption. Virtually no change in the communities before and after the eruption. So even a couple of kilometers from a major explosive event, the communities can survive if they have some kind of topographic protection helping them survive. It's not always the case, I'm afraid. As we've all seen, in January this year, we had the major eruption at the island, and that's what it looks like now. So I'm afraid that those survivors back in 2016 have probably all been totally obliterated. We're going to have to wait. We're going to have to wait before any expeditions are allowed into this area. The local scientific community in the area, the government, I should say, the government is very, very cautious about allowing people in. I'll just draw your attention in this image. You can see these diagonal streamers in the sea. This is pumice. This is pumice resulting from the eruption back in January. And I want you to just quickly remember that, because we're going to come back to it in a minute. Another place where carbonates can do quite well is when there is any kind of relief, any kind of bathymetric high, any kind of topography on the sea floor. These are very important areas. As you can see in this image, any material that's traveling at the sediment surface will move down the slope, and it actually bypasses these areas. So even in these areas of active volcanism, if you have topographic highs, bathymetric highs, then you have the chance of preserving your carbonates. Now, it's all very well and good saying that the volcanism happens and the volcanism buries the carbonates and the volcanism affects the carbonates. But what we need to think about is, do we see that in the stratigraphic record? And one of the problems is the preservation of the material, particularly where there isn't any cementation. Where we don't have cementation, and the action of wind, waves and currents will actually erode that unconsolidated material. It removes the evidence of the volcanic episodes itself, and eventually it will actually erode all the way down, and it will remove the evidence of the carbonate community. So all we will see maybe is carbonates, 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 or volcanism, volcanism, volcanism. We don't see that the two were living or occurring, I should say, together. So we don't see the evidence if we don't have the cementation. Luckily, in many cases, the mortality of the reef itself causes cementation to happen. The carbonate community, the organic decay associated with that burial changes the conditions, the chemical conditions immediately adjacent to the carbonates. This and reduced permeability enhances cementation. That enhanced cementation means that these systems are able to resist erosion, and by resisting erosion, they can be preserved. Of course, we will lose the portion of the stratigraphic record that was not cemented, but we do at least preserve this relationship. And that cemented surface can in turn become an important new substrate on which the next coral community can develop. The final of the killers, as it were, is the sediment gravity flows. And basically what we've got here is maybe, for instance, the lateral eruption or the collapse of an eruptive column. What happens here is it transfers quite often from the terrestrial to the marine environment. And as it does, what we'll find is there's an entrainment, a downslope carrying of the organisms from the different communities, from the shallower water into the deeper, from the proximal into the more distal. And this is going to result in a mixing. It's going to mean that the communities we see in these particular systems are not going to be autochthonous. In our previous example with the burial, we have an autochthonous system. Where we have a gravity flow, we're going to have an allochthonous system. We're going to have a lot of mixing of various communities down the slope. So if we're lucky, these are actually fantastic ways of preserving our carbonate communities, because once they are transferred down the slope into a deeper water setting, it enhances their chances of preservation. And then those organisms, we're going to have to decipher it and work out where they came from, what's their provenance, but we have got a chance of preserving that end community. And that end community may actually still not just be marine. It may involve bits of terrestrial material. I've often found bits of tree in reef deposits that have been transported and buried by these volcaniclastic flows that have been entrained and come down through valleys into the marine environment, bringing logs, bringing wood, bringing leaves into the reef community and burying the reef. One of the final things I want to think about, because I can see my time is almost up, is making a comeback. How do these reefs, how do these coral communities, how do these carbonate communities re-establish after the event? Well, the first colonizers are, of course, the opportunists, the ones that can get there quite rapidly, the ones that can survive on that new substrate, whether that's a hard substrate or a soft substrate. So those new survivors, those new opportunistic species. And once the opportunists are in there, we can go one of two ways. What we can find is that the community could maybe stay with a totally new community, totally different to the previous community. And that's what we see in the story on the left. Now, in the stratigraphic record, we may think that's a change in the wholesale environment, maybe temperature or water depth, but it's just to do with a different substrate. Or, as we can see in the image on the right, we may actually just revert to the previous community. And what is driving this quite often is the supply of juveniles, the supply of juveniles. And that supply can either be in the form of gametes, so basically literally juvenile organisms being brought down current. So if we've got a source of juveniles up energy, up current, they can be transferred down to our area and recolonize that area with the same sorts of communities. Another way that that can happen is where we have material brought in by pumice. And I showed you the rafting, that pumice rafting by Tonga Hunga Happy earlier. And that is what we see in the foreground of this image, is you can see pumice being transported down current. And that pumice rapidly, very rapidly, in a matter of days, has polyps corals, algae, it has all kinds of mollusks growing on it, and communities evolve on it until the pumice gets too heavy. When the community gets too heavy, the pumice sinks to the seafloor and basically seeds the seafloor. You can think of it as in your garden, you can plant seeds and grow flowers, or you can buy the flowers already grown and just transplant them. The pumice is almost a transplanting community, so it's very, very rapidly can seed a new area. Depends on what is up energy from you. Also, if you have, for instance, those lava flows we talked about earlier, you have those lava flows, they're fantastic substrates, nice hard substrates. Corals love these, sponges love these. All your sessile benthic organisms are going to start growing on these lava flows within, again, a few months. So that can be very, very rapidly. Now, I know I've gone through that very, very fast. I've put the reference here for the paper that I'm sort of discussing, and so you can look in there. There's many, many more things that I didn't have time to talk about today. And it's a very complex system, as I've tried to reflect in this figure that I've put together here. So this figure showing all those feedback relationships between the volcano, the atmosphere, and the ocean. All those are, and the communities themselves. And it's a very complex feedback, but perhaps our biggest problem is not the complexity of the system. It's a complexity in geology, really, or in science, I'd say. There's a strong disconnect, but I find that there's an awful lot of material out there that the geologists don't know about because it's in the biological community. There's an awful lot of material the biologists don't know about because it's in the geological community. There's also a strong disconnect within the geological community between the sedimentologists and the volcanologists. We don't talk to each other. Volcanologists, big bang, boom, they're really into the volcanoes and the sediments. The sedimentologists are into how those volcaniclastic materials come into the system. But then there's a disconnect between the sedimentologists in terms of the siliciclastic and the carbonate realm. And if there's one thing I've learned from the studies that I've been undertaking over the last 15, 20 years on these systems, is that we need to talk to each other. We need to go out and look at these reefs. We need to instrument these systems. We need to do this before the eruption happens, and we need to monitor the systems after the eruption as well. So this is all part of the key to these systems. Anybody who wants to get in contact with me, I'm easy to find online, or I'm also easy to find on Twitter, and there's a thing you can grab there for the Twitter if you want it. And I'm happy to take any questions. I see I've gone a minute over, so I'll shut up now. Thank you very much.